12b. And in 12, compare fission and fusion reactions. Fission and fusion reactions. Okay, so let's start. And nuclear fission is our first one. Fission, and that word fission means to split. So we're splitting the atom in this sense. This is all that happens naturally, not that we're making it happen. This is when large, unstable, there's the key word, unstable isotopes. Okay, I'm going to pause a minute right there. Isotopes. Isotopes, that word right there is a really important one. That's one you should remember, but I don't know that you do remember. But isotopes are atoms of the same element that differ in the number of neutrons. There's a sweet spot for the ratio between protons and neutrons in an atom. And if it's outside of that sweet spot, one side or the other, the atom isn't quite as stable. So this is when you have large, unstable isotopes of atoms that split into smaller, more stable atoms. Here's the key here, more stable. Remember that nature favors a lower potential energy. The larger unstable atom, it's got a lot of energy in it, and so it's got a lot of stored energy, potential energy, and it's naturally going to drop down to a lower energy level, which means it's more stable in that sense. So nuclear fission is when you have large unstable isotopes of atoms that split into smaller, more stable atoms, and they split, and when they do this, they're creating different elements. So you might have started out with one element, but you end up with two different ones after that. The original element is no longer the same thing. So this is when you're actually changing the identity of the element, not just chemical reactions where the atoms, the original atoms are all there and accounted for. You're actually changing the numbers of atoms, you're changing the types of atoms. So this is all about protons, neutrons, and electrons inside there. Okay, now that's nuclear fission. Nuclear fusion is just the opposite. Fusion means that you're going to combine. So when you fuse two things together, you combine them. So this is the opposite of fission. This is when you have smaller, unstable atoms. It's all about becoming more stable. So you have smaller, unstable atoms. And I'm going to put atoms in parentheses, isotopes. Remember, we were talking about different isotopes, so differing numbers of neutrons. It's always, again, that those number of neutrons that tends to make the atoms more unstable. So you have smaller, unstable isotopes that fuse to form one larger, more stable atom. That fuse, combine, to form one larger, more stable, it's all about that stability, more stable atom. And it'll be a different element. It won't be the same as what the two atoms you started out with won't be the same as what you end up with. So a different element is created. They used to call this transmutation. You changed elements here. This happens naturally in the universe. This is basically what happens in our sun. All the stars. Yes, remember the sun is a star. This is how it happens here. And in this case, you've got hydrogen combining with hydrogen to form not H2 like when we think in a chemical reaction, but it forms helium. So if we look at our periodic table, you're not just chemically combining them to form H2 like we see naturally all over the place. You're actually combining them, two different atoms of hydrogen, into one atom of helium. Totally and completely different than what we've talked about all year long. So really, really strange in that sense. Okay, the next thing I'm going to talk about briefly is I'm going to just go hit that word isotope again, because I think that's one that you guys might have lost a little bit of. These are atoms of the same element that differ in the number of neutrons. And just naturally, some isotopes are more stable than others. Some of these are stable, some isotopes are stable, so they're not radioactive, and some are unstable. And it's these radioactive ones, it's these unstable ones that are radioactive. Sometimes they call them radioisotopes. So you see that prefix radio on the front of it, think radiation, it's unstable. So an example of this again is when you have that hydrogen, and I'm going to write this and you guys will, hydrogen has a proton number is always down on the bottom. And the mass number is on the top here. Hydrogen typically has no neutrons, so it typically, the most common isotope has 0 neutrons, so it's got a mass number of 1 and an atomic number of 1. Remember seeing it like that? That's typically when the hydrogen is there. There are some hydrogen isotopes that still have an atomic number of 1. If it's hydrogen, it has to have an atomic number of 1. But it also has 1 neutron, so 1 proton plus 1 neutron makes it have a mass number of 2. There's also tritium, where in this case it's still hydrogen, so it has an atomic number of 1, and it's got 2 neutrons. So 2 neutrons plus 1 proton gives it a mass number of 3. So you have 3 different isotopes of hydrogen. This one is a lot more unstable than this one. And then the last thing I'm going to put on there again, and since you live close to Pantex, which is the final assembly plant for the nuclear bomb, any type of nuclear bomb itself that we make, it's kind of nice to know this. So we have Einstein that created or came up with his equation that relates energy and mass. So you can actually interchange energy and mass. They can convert back and forth. So energy is equal to the mass times the speed of light squared. If you add, now here's the deal. If you add the masses of the protons and the neutrons in a nucleus, and compare it to the actual mass of the nucleus, you find that the numbers aren't equal. There's missing mass. Okay, so that missing mass has been converted to energy to hold those protons and neutrons together. I mean, think about that. You know, the neutron's not a big deal. They don't have a charge, but all those protons are positive, and you're cramming all those like charges in there together. Don't like charges repel each other? There has to be some form of energy holding them together. And this is what they found. There is some missing mass, and that mass has been converted into energy, and that's what that strong nuclear force is that we just talked about on the last on the last notes, the strong nuclear force, energy. There's a video, it's a 1950s cartoon put out by the government, some arm of the government, that I'm gonna hook you guys up to online, and I really want you to watch that. It's really interesting. It's old cartoon, but it's really cool. So we find that when we have those nuclear bombs, when you split that atom open, this energy that was holding it all together is released. If you have a whole bunch of atoms and you release all that energy at one time, it's a huge amount of energy. I mean, think about the nuclear blast that you've seen pictures of. There's also a video called Trinity and Beyond, and I might not be able to link you to the whole entire video, but I can link you up to pieces of it. And what that is all of the nuclear trials that the U.S. government did. They filmed them, and maybe 15 years or so ago they declassified it, so they made a video out of that. So I'll link you guys to those videos so you can see some of those nuclear blasts that are there.